Hello, ladies and gentlemen. Welcome back. We're going to look at Chapter 6.3, Day 1. I'm going to pretty much do the whole Chapter 6.3 in this video. The next video after this is going to be going over problems. Really important that you make sure you watch that video because I'm going to go through and talk about different types of problems, and I'm going to do an AP question from a previous test with probability. All right, here we go, ladies and gentlemen. So, as I mentioned in the last video, there is a PDF. Okay, I would like you to read that PDF. You don't have to print it. It's right above the 6.2, I believe, video. So go back. It's called 6 Degrees of Freedom. I'm sure you've heard of that. Okay, here's the little cartoon that goes with that. Okay, so go read. It's a very interesting phenomena, 6 Degrees of Freedom. All right, and I'm sure you've all heard of that before. All right, let's keep rolling here. All right, so chapter 6.3. So chapter 6.3 starts off with the rules again, reminding us of the rules. Okay, rule 1, rule 2, rule 3, rule 4, and rule 5. And remember, rule 3, we can expand that and we can do the probability of A and B. We're going to subtract that out if they overlap. All right, so disjoint events, remember, you can simply add those together. Remember, disjoint events have nothing in common, okay? Nothing is in common, so therefore you can add those together. Okay, also known as mutually exclusive. Okay, here's an example. They do not share anything. These are mutually exclusive. They are disjoint. Okay, if they have a union, okay, which I talked about earlier, that's what the Venn diagram or the diagram would look like. They share something. And here's the extension of that rule that I just wrote in, right? So the probability of A plus the probability of B minus the probability of A and B. Okay, here are the symbols, folks. Ooh, I should write, yeah, I need to point this out. Okay, a big fat looking U is the symbol for OR, and the upside down big fat U is the symbol for AND. Okay, so make sure you understand what those symbols are when you see them. All right, we're going to look at the Venn diagram worksheet. So again, this is right above the video if you want to print it. So again, disjoint, this rectangle is representing our sample space. And again, disjoint events or mutually exclusive events means they do not overlap. That simply means we can add those events together if we're asked about a probability. Okay, you can add the events together to find the probability because it's an OR situation. Okay, the union of events, we just saw that. That's where they're overlapping. And then this is the A and B. So that would be the probability of A plus the probability of B. But you cannot, if you add those together, you would add the overlapping part twice. So you have to subtract that part out. Okay, let's look at some real life situations here. So, who reads the newspapers? Again, if I'm going too fast, please hit the pause button. In a large apartment complex, 35% of the residents read USA Today, 20% read the New York Times, and 5% read both. All right, make a Venn diagram. So we're going to go ahead, we're going to make 2 circles. Okay, I'm going to let this one represent the USA Today. I'm going to let this one represent the New York Times. Now, I always start in the middle, folks, and always use the decimal. So, reading both newspapers is 0.05. Now, be careful. You already have 0.05 in the center. Okay, USA Today is 0.35, but you already have 0.05 in the middle. You've got to take that out. So the rest of the circle will be 0.30. Okay, same thing with the New York Times. You already have 20, or there's 20% for the New York Times, but you already have the 5% in that circle. So you have to take that out. So that's going to be 0.15. Okay, however, we're not done because some people, ladies and gentlemen, don't read any of the newspapers. Some people don't read any of them. So if we take what's in the circles and we add those together, okay, we are going to get, let's see, I believe that's going to add up to 50, right? 0.50. Okay, so half of the people are reading the newspaper. That means half the people are not. Okay, that would be on the outside of the circle. Not, okay, not reading those papers. That's on the outside. 50% are in both circles altogether, and 50% are on the outside. So what percent read only the USA Today? That would be, well, since it says percent, I'm going to go ahead and put those in percents. 30%. What percent read only the New York Times? 15%. What percent read neither? That's the 50%. All right, I'm going to keep going so I don't have this video super long. Okay, number 2. Suppose 60% of all customers in a large insurance agency have automobile policies with the agency. 40% have homeowners policies, 25% have both. If the customer is randomly selected, what is the probability that he or she, okay, I'm always going to start off by drawing my Venn diagram. I'm not even going to read the questions. Okay, so 60% have automobile, so I'm going to put auto. 40% homeowners, I'm just going to put home. Always start in the center, which is 25% or 0.25. Okay, 60% are auto, so again, I'm going to have to take 0.60 minus the 0.25. And let's see, I believe that is going to be, let's see, we borrow, put a 5, 1, 5, that's going to be 0.35. Yep. Okay, then I'm going to need to do the home, so I'm going to take the 0.40, take away the 0.25. Okay, well, I believe that is going to be 0.15. Yep. I got to make sure I do my math right. Okay, then I'm going to go ahead and figure out, well, what's left over for the people that do not have it. Okay, well, if I take my 0.35 plus my 0.15 plus my 0.25, okay, well, let's see, 35 and 15 makes, let's see, that would be 40, 50, and then I believe that would be 75. Okay, let me double check here. I just don't want to make any silly mistakes in my math. Sometimes I'm shooting this video early in the morning and sometimes my brain is not working at 100% yet. Yes, okay. So what's left over? 0.25. All right, so has at least one of these two types of policies. Okay, that means has one or both, right? That means one or both. Okay, well, we figured that out right here. I added those three numbers together, one or both. Has neither type. Well, that's the complement, 1 minus the 0.75, which I figured out is the 0.25. Okay, has exactly one type of policy. Okay, so the probability of auto or home. Okay, well, folks, auto is just, there, let me switch colors here. Auto is just 0.35 and home is just 0.15. Okay, notice I am not counting both of them. I'm doing one or the other. Has exactly one, but not both. So let's see, that's going to be 40. Looks like that's going to be what, 50? and that would be our answer. Okay, exactly 1. All right, let's keep rolling. All right, there are 2 traffic lights on the route used by a certain individual to go from home to work. E donates the event that the individual must stop at the first light and define the event F in a similar manner for the second light. Suppose the probability of E is 0.4, the probability of S is 0.3, the probability of E and F is 0.15. All right, so I think part of the point of this one is being able to use the appropriate symbols. All right, so E and F. So in the center is the 0.15. Okay, so what's left over for E? So we got to take the 0.40 minus the 0.15. Let's see, and I believe that that's going to be 0.25. So this is going to be 0.25. Same thing with the F. We're going to take the 0.30, take away the 0.15. Well, that's 0.15. All right, what's left over for the rest of that Venn diagram? So I'm going to go ahead and I'm just going to do this real quick. I'm going to add these 3 together. And let's see, that's going to be 0.55. So what's left over? What's the complement? That would be 0.45, right? 1 minus the 0.55 gives us what's left over. Okay, so what is the probability that the individual must stop at least 1 light? Okay, that means 1 or both. Well, at least 1. Okay, so the probability of 1 or both, that would be what I already did right here, folks, I believe. Okay, you got to stop at 1 or both, so at least 1, so that's going to be 0.55. Okay, it doesn't say give it as a percent, so I'm going to leave it 0.55. What is the probability that the individual needn't stop at either light? Okay, well, that would be this one, right? 0.45. It's not going to stop at any light. What is the probability the individual must stop at exactly 1 light? Okay, well, exactly 1 light would be the E or F, but not both. So that would be the 0.25 plus the 0.15. And that would be 0.40, I believe. What is the probability that the individual must stop at the first light? Okay, well, that's the 0.25. Well, actually, let's think about this. What's the probability the individual must stop at the first light? Nope, I'm gonna change my mind on that one, folks. That would have to be the 0.40, because that's what it says right here. The probability of stopping at the first light is 0.40. Okay? Yeah, it doesn't say, so you have to include the 0.15 with that. All right, let's keep rolling. All right, oh yeah, I'm supposed to go back to that problem on the previous one. Okay, I think with what I've done so far, you have a good idea of how to do these, so I'm not going to do this problem. So if you want to go ahead and add it to your notes, go ahead, ladies and gentlemen. The problem that I skipped the last time in a video, I believe I have it right here. Yes, it is. It's right here. This is the one that I had skipped. Okay, but from what we did already with the examples I gave you, I don't think I need to do this one. Okay, if you want to go ahead and give it a shot, go ahead, because I don't want this video to be like an hour long. Okay, but I am going to look at number 5 because this one deals with 3 circles. All right, because we're dealing with coffee, tea, and cola. When we do a Venn diagram with 3 circles, it has to look like the Olympic rings. And I know I went outside the rectangle, but that's okay. So here's all of our information. Take a moment, pause the video, and read through them. Okay. always remember we got to start in the middle. Oh, and I need to label these. So I'm going to label this, let's see, I'm going to label this coffee. I'm going to label this tea, and I'm going to label this cola or pop. All right, always starting in the middle. So when I read through this list, I see this one right here, 5% drink all 3 beverages. Check. That one's done. Okay, now I have to start filling in things around it. So let's see here. 5% drink only tea. I can do that one. 5% drink only tea. That would go there. Let's see. Let's go to this 25% drink both coffee and cola. 25% drink coffee and cola. Oh, I can do that one. Let's think through this. So 25% drink both coffee and cola. Well, you'll notice that there is the 0.05 is already in that part. So here, let me do this one in red so you can see what I mean. So I'm going to do this. See this part? See that part? That's the coffee and the cola. The 0.05 is already in there. So what I have to do is I have to take that out, ladies and gentlemen, which gives me 0.20. So that's going to go here. Okay, hopefully you can see that. So that one's done. All right, let's go to a different color here. 15% drink both coffee and tea. Yep, I can do that. So here's the coffee and tea right here. I just outlined in green. Okay, look at it. So same thing. I'm going to have to go take 0.15 minus the 0.05, which is going to be, whoops, that's a 5, which is going to be 0.10. So I'm going to put 0.10 here. Okay, that one's done. Now I should be able to do the rest of these. Let's start with the coffee. 55%, let's go with orange. 55% of the adults drink coffee. Well, here's the coffee circle. Okay, and I already have 3 of those in that circle. And let's see, those add up to 0.35, right? If I add those 3 together, that's 0.35. So what I have to do is I have to take away the 0.35 to see what's left, and I believe that's going to be 0.20. All right, that one's done. I'm running out of colors here. Let's go with pink. All right, 25% drink tea. Yep, I can do that. So here's the tea. So the 3 that are already in there add up to 0.20. So I'm going to go ahead and take 0.25 minus the 0.20, and that's going to be 0.05 that's left over right here. Cool. So let's see, yep. Okay, well, let's see. A color, I'll use black, yep. 45% drink only cola. Well, again, here's the circle for cola. And if I add those together, that adds up to 0.30. Okay, so I'm running out of room here. So 0.45 minus the 0.30 is going to be 0.15. Cool. I like this problem, really. All right, now, there are some people that aren't going to drink any of these. So I'm just going to go ahead, since I'm running out of room, folks, I'm going to go ahead and take my calculator, and I'm going to add these up. All right, I'm going to add these up. So I'm going to go ahead and take 0.20 plus, here I'm going to use my keyboard directly, plus 0.10 plus 0.05 plus 0.05 plus 0.05. Yes, I could probably have added those in my head. Plus 0.20 plus 0.15. And I think that's right. Hopefully I did that right. Let's see, 20, 40, 50, 60, 70, 80. Yep, I believe so. So they add up to 80, right? Okay, they add up to 80. So what's left over? Okay, 0.20. So what percent drink only cola? Okay, well, only cola, that's the 0.15. Actually, it wants a percent, so let me put that as a percent, 15%. What percent drink none? We just figured that out, 20%. Whew. All right, let's keep rolling. Okay, we're going to skip over that. I believe that's all that's on this page. We already did the tree diagrams from the last lesson. All right, here are some more problems. I am not going to do these at this time because my video is going to be long enough the way it is. All right, so we're going to keep right on rolling. Conditional probability. All right, ladies and gentlemen, they really like their conditional probability on the AP test. So we need to make sure we do this. Make sure you watch that next video because I'm going to do examples, more examples of conditional probability. So what is the probability that A is greater than 0? The conditional probability of B given A is. So you'll notice there's a vertical line right here, ladies and gentlemen. So that's a conditional probability. The probability of B given, that vertical line stands for given A. So to find it, you take the probability of A and B and divide it by the probability of A. Now, caution. Be sure to keep in mind the distinct roles in the probability of B given A of the event B whose probabilities were computed and the event A that represent the information we are given. You're going, what? Okay. The conditional probability makes no sense if event A can never occur. So we require that A must be bigger than 0 whenever we talk about the conditional probability. So if the probability of A is 0, you can't do this. It has to be bigger than 0. All right? All right, so, oops, I didn't want to do that. I wanted to make this a little bit smaller here. All right, so students at the University of, so here's an example. Students at the University of Harmon received 10,000 course grades last semester. Da-da-da-da-da-da. Okay, take time to read through that. We're given a table of values. Okay, and then we're given finding the probability of liberal arts. Okay, so take time to look at this example. I'm not going to go into detail because my video is already 22 minutes long and I got to get through a bunch of other stuff. The definition of conditional probability. Okay, so here it's showing how to use that conditional probability and where they came up with the numbers. Okay, they found this information and then they use that information to find the probability of that condition. All right, again, look at example 6.25 and example 6.28. All right, conditional probability time. This is above your above the video if you want to print it. So we're going to be using a table. In this table, we are given the ages or age ranges and marital status of women. And please realize that this is in thousands of women. So this 19 is 19,000. So here we go. What is the probability that a woman is married? Okay, well, there's 999,585 for a total. That's actually million, folks. But above, okay, married, so it's this over this. So 58929. Okay, and then that's about 0.59. Next one says, what's the probability that they're 18 to 24? Okay, well, that's the age group, folks. So you got to look at the column. So the total of that age group divided by the whole total. So that is 12,614 divided by the 99585. and that's approximately 0.127 or 0.13. Okay, the next one says, well, married, whoops, I didn't want gray, I wanted green. Married and that age group. Okay, well, married and that age group, that's going to look at your row and column. That's the 3,046. And that's going to be over the total 99585, which is approximately 0.03. Now, those are not conditional yet. Okay, here we go with the conditional. Married, given that they are in this age group, okay? Given the information that. So the condition here is married given that age group. So when we look at that, okay, since it's this age group, ladies and gentlemen, let's see which color haven't I used yet. Let's use orange. Okay, we look at this age group only. We look at this age group only. I don't care about the rest of the table. All right, that age group only, and they're married. All right, so you take the married and divide it by the total of that age group. So that's going to be, I'm going to go over here, 3,046 divided by the 12,614, which is approximately 0.24. Okay? All right, I'm going to do one more set with you here, and then we're going to talk about the independence. And hopefully this example will be good enough. There are more problems that you could practice with, but if you need to, just rewatch this part of the video. Hopefully just one of these examples, or two of them, I'm going to do another one here, will be enough. All right, so what I'm going to do, ladies and gentlemen, is I'm going to go ahead and let me erase this up here really quick because I'm going to mark this up again. Okay, but I'm going to go down. So now I'm going to go to, they're at the probability of at least 65. Let me start with green, at least 65. Again, no condition here. So at least 65, ladies and gentlemen, that would be all of them. So 18,262 divided by the 99585. So the 18,262 divided by the 99585. Okay, you can go ahead and figure out the decimal for that. Again, pause the video if I'm going too fast. Okay, the next one, widowed and at least 65. Okay, so widowed and at least that age is this. Now, there's no condition here. It just says they're a widow and they're at least 65. So you're going to take the 8636 and divide it by the 99585. So 8636 divided by the 585. Sorry about that. And you can find the decimal. All right, now condition. Okay, I'll do this one in orange. Widowed given at least 65. That means, ladies and gentlemen, I only want to look at the age 65 group. I only want to look at this age group, only that age group. That's the condition. And I want to look at the widow, okay? So that means, ladies and gentlemen, I'm going to take the 8636, but I'm going to divide it by the 18,262. All right, so the 8636, and we're going to divide it by the 18,262. Now, whoops, sorry, I wrote that in the wrong spot. Let me back that up. I didn't leave myself much room, so what I'm going to do is I'm going to draw an arrow. and I'm going to put the 8636 divided by the 18262 here. All right, this next one is another condition, widowed, but in this age group. So I only want to look at that age group. That's the condition. Look at only this age group, and I am interested in the widow. So widow, so 2424 divided by the 68709. So 2425 divided by the 68709, and then get your decimal. All right. I know I'm going fast, but again, I'm up to 30 minutes already. So actually, let's go with purple. Put a star by this one. And I'm going to go over this again in the next video because this is really important to understand. I think they throw this on the AP test every year. Are the events widowed and at least 65 independent? How do you know? Okay, well, ladies and gentlemen, the probability of widow and at least 65 equals the probability of being a widow times, I'm using my rules here, times the probability of at least 65. Okay? Now, let's take a look. So let's take a look right up above here, folks. We figured out the probability of widow and at least 65. Okay, let me draw an arrow to that, showing you right here. See, right here, we figured out that probability. Yes? Okay, we didn't actually put the decimal there, so I'm going to need to put the decimal there. So when we do that, that's approximately 0.09. Okay, 8636 divided by 99585 is approximately 0.09 when you round it. Okay, rounded 2 decimals. So this is 0.09. However, if I take the probability of being a widow, okay, folks, the probability of being a, whoops, let me back that up. The probability of being a widow is going to be 11080 divided by the 99585. Okay, I'm going to figure that decimal out quick. So the probability of being a widow, okay, 11080 divided by 99585 is, let's say, 0.11. The probability of being at least 65 years old. Okay, the probability of being at least 65, let's switch to pink here, at least 65, that's going to be 18262 divided by 99585. So let's figure out that decimal. So 18262 divided by 99585. So we're going to round that to 0.02. 0.02. Okay, again, let me show you what I'm doing here. So the probability of widowed and at least 65, I found this from the table, that probability is about 0.09. I found the probability of widow separate and the probability of at least 65 separate. If I take the 0.11 and the 0.02, ladies and gentlemen, and I multiply those together, 0.11 times 0.02, I get 0.0022. Okay, I'm not going to round that one. They do not equal each other, folks. No. Okay, they do not equal each other. What does that mean? Okay, well, ladies and gentlemen, since the probability of A and B does not equal the probability of A times the probability of B, these events are not independent. Wow. That means they are dependent on each other. If they equaled each other, we can say they're independent. If they equal each other, we can say they are independent. But since they are not equal to each other, they are not independent. Okay? Highlight this problem, star it, do something to remember that. If you want to write the other form of that, so we could say if the probability of A and B equals the probability of A times the probability of B, then they are independent. But since they did not equal each other, they are not independent. That means that they are not mutually exclusive. They are not disjoint. All right, let's keep rolling here. Ooh, I'm up to 37 minutes. Man. All right, these are just some more examples. I'm not going to go through it. I think the examples that I went through are good enough. These are interesting. Okay, I like doing these because they deal with different things, but it's the same process of setting up your conditional probability and probabilities based on a table. All right. All right, let's see. Do I want to do this conditional probability? No, we're not going to do those at all. Those deal with the tree diagrams. We already did tree diagrams. So this is just a reminder. General multiplication rule for two events. All right. Oh yeah, I want to go through that PowerPoint again. So I'm going to bring up that PowerPoint. There's a video I want you to watch on Khan Academy. Please watch that. And let me bring up that PowerPoint really quick with the James Bond, with the conditional probability. It'll make more sense now that I've done that example. So I'm going to go ahead and pull that up. All right, so I went through this before, so I'm going to go ahead and jump ahead to that conditional probability. Okay, so we looked at that. All right, so here it is, right? What is the probability that a randomly selected driver traveling to San Francisco is planning to wear flowers in his or her hair? All right, well, S is the event that they're going to San Francisco. W is the event that they're planning to wear flowers in their hair. So this is the conditional probability, which I just taught you. Okay, the probability of wearing flowers given that they're going to San Francisco. So that's the probability of wearing flowers and going to San Francisco divided by the probability of San Francisco. So the probability of this and this is 128 out of the 800 divided by 376 divided by the 800. And again, we got that information from, oh, right here. I went past it. Okay, right here. Okay, moving on. So, based on these data, is there evidence that going to San Francisco and wearing flowers in your hair are independent? Okay, so we find that the probability, the conditional probability from above is — the probability of wearing flowers in your head is that 128 plus the 85, which is 0.2663. They do not equal each other. Okay, so it seems doubtful that going to San Francisco and planning to wear flowers in one's hair are independent. Okay, it is doubtful. Okay, that means they, okay, now, just go with what it says there. It seems doubtful that going to San Francisco and planning to wear flowers in one's hair are independent. All right, hopefully that makes a little more sense. Sorry if I confused you a little bit there. But this video is 40 minutes long, and I think we need to end it soon. So let me get out of this screen just to make sure that I've gone over everything. Let's see. Again, there's a Khan Academy video I want you to watch. Please watch that. It's underneath this video. And yep, that's it. All right, folks. So again, the next video is going to be me doing more examples of probability, and I'm going to include a AP question in there. Make sure you watch it. Okay, I'm not going to give you any new notes. I'm just going to give you examples. All right, we'll see you soon.